Please welcome to the stage AAAS CEO and Executive Publisher of the Science Family of Journals, Sudip Parikh.
Good evening, everybody. It is so great to see you all. I know that you are making a sacrifice to be here because today is Valentine's Day, so happy Valentine's Day. Our time together here in Phoenix is about to come to a close. We still have two great events left for all of you. I get to remind you that we are gathering thanks to the support of a group of wonderful sponsors and partners. I want to take just a moment to recognize them one last time. The 2026 annual meeting host university, Arizona State University, the Jimmy and Rosalind Carter School of Public Policy at Georgia Tech, the George Washington University, Florida International University, the Gordon and Betty Moore Foundation, the Science Philanthropy Alliance, UL Research Institutes, Digital Science Research Solutions, KFUPM, Morgan State University, and the American Institute of Physics. Our deepest thanks to all of these organizations for their support of this year's annual meeting. Now, I also want to take one last opportunity to thank the Annual Meeting Program Committee, chaired this year by President Teresa Maldonado. I want to thank the entire program committee for this exceptional dedication that they put in. It's a lot of work to put a meeting like this together, and they do it, and I really appreciate it. So thank you to all of them. And then lastly, I want to thank the entire AAAS team. For the things that you saw that went smoothly, I want you to thank the AAAS team. For the things that didn't, I want you to thank me. If there are things that didn't work, I want to hear about them, but tell me, don't tell them. They worked hard. We started off this meeting saying that there's a moment of challenge, and that continues to be the case. But I hope that you found that finding a little bit of community, a little bit of time together, a little bit of time to look at science and say, I remember why I'm here. I hope that was valuable to you. Now, on to this evening's show. I am really excited about tonight because, I got to tell you, I love astronomy. And our speaker for this evening, Dr. Bob Blum, directs operations at the Vera C. Rubin Observatory. Now, if you haven't heard about it, it's a brand new astronomy and astrophysics facility jointly funded by the United States National Science Foundation and the U.S. Department of Energy Office of Science. And it's on Cerro Pachon, I hope I said that correctly, in Chile. It's named after astronomer Vera Rubin. Now, Vera Rubin provided the first convincing evidence for the existence of dark matter. And at the end of 2025, the team at Science magazine named the Rubin Observatory one of the breakthroughs of the year. Now, Dr. Blum will tell you more about the observatory. Now, the coolest part about the observatory that I understand is that it records the entire sky in unprecedented detail every 3 days for the next 10 years. Pretty extraordinary. But before that, a little bit about Bob. Dr. Blum joined the Rubin Observatory team in 2018 after 21 years at the National Optical Astronomy Observatory. Now, 10 of those years were as its deputy director. Prior to that, Bob spent 10 years at the Cerro Tololo Inter-American Observatory in Chile. Bob's research interest is large survey science with a focus on studies of the Milky Way and the local volume. And if you don't know what that is, come see me afterward. Dr. Blum holds bachelor's and master's degrees in aeronautics from the University of Washington and a PhD in astronomy from the Ohio State University. After Dr. Blum's talk, he's going to be joined on stage by my colleague and friend, Dr. Jennifer Wiseman, who will engage Dr. Blum in a fireside chat. Now, Dr. Wiseman is an astrophysicist who studies the process of star and planet formation in our galaxy using radio, optical, and infrared telescopes. She has worked with several international observatories and is currently a senior astrophysicist at NASA's Goddard Space Flight Center. Jennifer is also interested in science policy and public science engagement. She's a fellow of the AAAS. She's a current member of the section steering committee for the AAAS section on astronomy, and she served as a AAAS APS Congressional Science Fellow and is an elected counselor of the American Astronomical Society. And many of you may know that for a long time, Jennifer directed the AAAS Dialogue on Science, Ethics, and Religion. She enjoys sharing the excitement of scientific discovery and has appeared in many venues, including the New York Times, the Washington Post, Nova, and National Public Radio. But now, please join me in welcoming to the stage Dr. Robert Blum.
Good evening. It's a pleasure to be here. I want to acknowledge one thing right off the bat. Many of you came tonight, or maybe even this week, because you thought you were going to hear from Brian Greene, and I'm not Brian Greene. He's a fantastic scientist and a really great communicator. I'd like to hear him too. And while I won't replace him, it's an honor to be here to fill in tonight for you all. So my name is Bob Blum. I am the director of the Vera C. Rubin Observatory. I work for an organization called NOIR Lab, National Optical Infrared Research Laboratory. That's a mouthful. It's actually just NOIR Lab, and we're down the road in Tucson, Arizona here. I also work very closely on this project with colleagues from SLAC National Accelerator Lab in California. I wanted to start out by just broadly telling you what our mission is with the Rubin Observatory, and then I'll get into the details of how we're going to accomplish it. We want to produce an unprecedented astronomical data set for studies of the deep and dynamic universe, and we want to make that data widely accessible to a diverse community of scientists and engage the public to explore the universe with us. Engaging the public is absolutely important as we go forward with science in this country and around the world, more so now than ever. And Rubin will play a big role in that from the astronomy point of view. We will bring the night sky to life. The Vera C. Rubin Observatory will revolutionize the way we think about and explore the cosmos, engaging the public, but also the scientists in ways that they haven't been able to do before. The instrument that we will use to bring the sky to life is something we call the Legacy Survey of Space and Time. That's the actual survey we're going to do over the next 10 years. We will repeatedly scan the sky for 10 years, covering it about every 3 nights, and we'll use the largest digital camera ever built in the world to do it. We think of it as creating an ultra-wide, ultra-high definition time-lapse record of our universe. In fact, you need about 400 ultra-high definition televisions to see one of our images pixel for pixel. We also like to say it will be the greatest cosmic movie ever made. Like all big projects, this one started with interesting ideas. It started just with people thinking about what they can do. Tony Tyson is a physicist at the University of California at Davis. And more than 20 years ago, he was observing in Chile on one of our other telescopes with the biggest digital camera of that time. And he was trying to understand dark matter by observing galaxies in the distant universe. And he thought, if we could dedicate a telescope that had a much bigger field of view, but also a wide aperture to capture more light and go deep into the universe, we could make a lot of progress on dark matter. Big ideas need big solutions, and one of the big solutions was how to build a telescope that could do that. Most telescopes look at a tiny, tiny part of the sky. Especially the bigger the telescope is, it's more often the case that it can only observe a small part of the sky. So it was a challenge to do both a wide field and a wide aperture. Roger Angel at the University of Arizona came up with a concept of 3 mirrors that would do it. That concept is actually drawn on this napkin, and we still have the napkin somewhere. I'm not exactly sure where it is. But from those beginnings, we've come a very long way to just an amazing facility that's going to transform astronomy and astrophysics in the next decades. We are also very, very proud that this telescope, this observatory, is named after Vera Rubin. She was literally a cosmic trailblazer. She provided the first systematic evidence of dark matter that had existed in our universe, and you needed it to explain what you observed in the rotation curves of galaxies. She's also a passionate advocate for women in astronomy, and the things she has done haven't erased all the problems or lowered all the challenges for women and others in astronomy, but they sure have made a difference. This is the first big observatory in the US named after a woman. We're very proud of that, and so we like to encourage our colleagues and the public never to shorten it to an acronym. We always say the Vera C. Rubin Observatory or the Rubin Observatory. The facility has been constructed on a mountaintop, as you just found out, in Chile. It's called Cerro Tololo. That was very well done. It's actually in the front range of the Andes, the Chilean Andes, in about the middle of Chile along its coast. And it is near the Pacific coast in a seaside town called La Serena, where our headquarters are. And as we heard also, it was jointly funded by the National Science Foundation and the U.S. Department of Energy. They have supported us for more than 2 decades to get this to the place that it's been, and we're enormously grateful for that support. The operations partners with which this program is run are Noir Lab, that I mentioned earlier, and also the SLAC National Accelerator Lab. So jointly run, kind of a 50-50 partnership between NSF and DOE. That's also been something that's led to our success, I think. So how are we going to capture the cosmos? How can we capture the sky and understand the history and evolution of the universe? It takes at least 3 things in our case, and we have them now. It takes a wide field of view. We have the world's largest digital camera. This is an image of it at SLAC National Lab before it was shipped to Chile just a little while ago. We need a telescope that's very rigid, very strong, and very fast. This telescope moves around the sky faster than any professional telescope currently in operation. And it's very rigid so that when we move quickly to a new place, it's ready to go and can immediately take images. We just relentlessly need to keep moving on the sky every second that we're up there. Seconds matter. If you do the math, we're taking an image every 40 seconds. Over 10 years, if we can gain a second somewhere, that's a significant number of extra nights that we'll get to observe. And then it needs to go deep, so it needs to be a large aperture telescope to gather lots of light so it can see faint objects. If you put that all together, this is what you get. You get a machine that can scan the sky repeatedly. Think of this as making one big image every 3 nights from that single image adding up. And then over 10 years, we'll be able to stack about 1,000 of these across the sky. And so not only are we seeing things happen every night, but as we go through the 10 years, we can stack images up and go deeper and deeper. And find very faint objects and new and interesting things. This telescope, we like to think of it as a discovery machine or a discovery engine. It will detect many new things that are changing. Asteroids and comets that move across the sky, supernovae that explode, pulsating stars, hidden stars and galaxies that are very faint, completely new things, things that we maybe have not even seen yet. The way we can find those, I'll let this play again, is that we build up these deep images of the sky. Think of that as a template image. Every time we go back and hit that place on the sky again, we can subtract the template from the current image, and we can, I'm not sure I can get it to go again. No, it doesn't want to do it. Anyways, we subtract the template from the new image, and what's left is just the things that have changed. Either they've moved in position or they've changed in brightness, like a supernova going off. So every night we will detect those objects and we'll make them available for future follow-up. So I wanted to have a little fun tonight. We're just at the precipice of getting this thing started, starting the survey, starting the science that we've been waiting for 2 decades, and a lot has happened in the last couple years. And I'd like to go through some of those things to show you kind of what's been going on at the telescope for the last period. It's a decades-long project. It started with scientists getting together with ideas. They built a science case. That science case resulted in detailed designs. Those detailed designs were put into building subsystems. All those subsystems have come to Chile, to the mountaintop, in the last 2 years. And what I'm going to show you next is some of the major milestones of those systems coming to Chile and being integrated and making one system. We often talk about observatories and telescopes. Rubin is actually a system. It's the telescope, it's the camera, it's the data management, it's the internet that gets us from images from Chile to California to get processed. The main mirror of the telescope is obviously one of the key things. So this actually was brought out of storage where it had been safely kept for a number of years on the mountaintop next to the observatory, waiting for the point where we could put it on the telescope. So the journey actually started about in 2019 when this giant mirror, this is our primary mirror, about 8.4 meters in diameter, left the University of Arizona Richard F. Karras Mirror Lab. It was put on a truck. You can see it there in its container on the truck. That's on I-10, actually. Many of you are probably familiar with that going east. And we drove it to Houston. In Houston, we put it on a giant ship, and then it sailed south to Chile, docked at a port that was close to our observatory, and then over several days, because it's a very wide load, we made it up to the observatory. And what I'll show you next is actually a time lapse of this last part of the journey. You see it reflected here in the lower image, where the mirror has come out of its storage location right nearby, and it's the last part. We get into the facility, and we hope it stays there forever. When I saw these images that day, kind of live as it was happening, I was like, wow, that looks like it's really close to the edge of the road. It was never quite as close. It looks closer than it was. But you can see it took two giant tractor trailers to pull it up there, get it up that, not that steep a hill, and around the corner and into the facility. So that was an amazing day. That was back in 2024, just about 2 years from today. So the first thing we had to do was put the mirror on the structure that would hold it to the telescope. That's what you see at the bottom of this image. That the lighter green or teal color is called the mirror cell. So that's the structure that actually holds all the equipment that will control the mirror when it's used and physically attaches it to the telescope structure. You're seeing this blue coating on there. That was just the storage coating. It was on there to protect the surface of the mirror. And what you're seeing is it's partially under a giant dome. That dome is the vacuum chamber that coats the mirror. In fact, it was under there for a few days as we stored it in this place. We're now pulling it out. Right after this, we cleaned that blue goo off the mirror, and then we put it back into the coating chamber, sealed it up, drew vacuum, and put a very, very thin layer of silver and a few other protective layers on it. And now you can see the full mirror here. You see that shiny surface, and even one of our team right in the middle hole of the mirror, and the rest around. So it was a fantastic job. They spent many years designing, building, and testing this chamber. And the reflectivity of this mirror as measured after it came out was one of the best, very best that we've ever seen in a large optic in astronomy. So we're really excited. Really provides tremendous throughput across the wavelength that we're seeing. Now I'm going to show you a fun picture, a fun time lapse of the mirror being moved from that lower level of the facility 5 floors up and onto the telescope platform. I'll let it go a couple of times. What you're seeing is it's coming out of our integration level on 3 and going up this elevator that's 5 stories tall. You can actually see in the end here that it lifts the roof off of the elevator at the top, and there's a door in the back of the dome or the enclosure that it slides through, and then over some tracks and onto the telescope platform and under the telescope. That was a really fun day. That took about it was lifted up and put into the position in the morning, and then that yellow cart has actuators that actually lift the mirror, get it right up underneath the telescope, and then giant bolts attach the whole thing to the structure. So a giant telescope with mirrors needs a great instrument. And so our camera was built in California at the SLAC National Accelerator Lab, and it got a charter flight from SFO, San Francisco International Airport, to Santiago de Chile. and then took about 2 days to ride very carefully. We don't think we needed it, but the Chileans were very excited, so they gave us a police escort as well along the highway. Anyways, it made it up without incident. The team was ecstatic to unpack it from its container and start working with it. Now, this was in May of 2024, and it took about 10 months or so to get ready to put it on the telescope. So after the shipping, had to reinstall a bunch of things. We wanted to retest, so we actually did optical testing and other things in a clean room here on the summit of the facility. And retested it, re-verified, got it all ready, and then eventually took it up and put it on the telescope. So that was by March, after the Christmas holidays and everything, things got ready. Then we got serious and we really got it ready to go. And then by March of 2025, so just a year ago, it was all ready to go. What you're seeing here is the camera installed on a structure, that teal structure, steel, that will connect it to the top end of the telescope. And so it's cantilevered out the full length of the camera. It's about as big as a small SUV. That front mirror, or front lens, we call L1 or lens 1, is 1.6 meters in diameter. So just about, I'm just barely taller than that lens. Anyways, it was all checked out and ready to go, and then we installed it on the telescope. This will loop back to the beginning, and I'll let it go a few times. So you're looking at the telescope as it's pointed at horizon. The camera is being lifted carefully up with this big yellow lifting fixture that it cantilevers off of, and then it's slowly turned and inserted through the top end of the telescope, actually through the secondary mirror, and pointing downward if the telescope were pointing upward. That took a couple days. We took 1 day to very carefully move the whole thing up to the observing floor, then we left it there, and then we came back the next day and lifted it and put it on the telescope. You can see it still has a lens cap there for protection as we got ready. So we got it all hooked up and under vacuum and cooled down. The detectors in this camera run at minus 123 degrees C, so everything is embedded inside a vacuum chamber. What you're looking at here is if I was standing in the middle of the telescope with the main mirror behind me, I'm looking at the camera and I'm looking toward the secondary mirror. That's the shiny circle toward the bottom of the image. And so this is the completed telescope ready to go on sky in April of 2025. What you're looking at here is the telescope pointed straight up at zenith. So if the enclosure, the dome of the observatory, was open and looking at the night sky, the telescope would be pointed right overhead. So light comes in through the opening of the enclosure, and that large mirror collects all that light, bounces up to the secondary mirror. It follows down the secondary mirror. And if you've been paying attention when I showed you the picture of the silver-coated mirror, it looked kind of funny. It looked like one big surface on the outside and then a more steep dish in the middle. That's the tertiary mirror. Think back to that napkin. It was 3 mirrors. In the napkin, originally, they were 3 distinct mirrors. We found a way that would really help controlling the whole thing if we built 2 mirrors out of 1 piece of glass, so that's what we did. So the first mirror and the third mirror on the same glass substrate, but it's still 3 different mirrors. So comes in, first mirror, second mirror, third mirror, and then bounces up into the camera, which is always facing down at the main mirror. So with all that ready, April 15th, less than a year ago, we were ready to go on sky. You see this beautiful image of the facility that night. The moon was shining on our enclosure. That's why it looks bright like that. And we're looking out over the Pacific Ocean at sunset. So it was a great night to start the whole thing off. It was a tremendous moment when we opened the dome shutters and put the camera on sky and took our first image. That's the first image we ever took. What you're seeing here on the top is the full focal plane, all the detectors that gather light through the full optical system. So these are detectors that are in your phone, only we have many, 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 many more of them. On the upper left there's a few that weren't turned on. They're turned on now. That was just a small technical glitch. But what you see in the bottom is the central 9 detectors, just as a blow-up, and you can see those circles. What are those circles? Those circles are stars, and they're out of focus, and so they're formed a donut in the image. If they were in focus, they'd form a point. So, okay, that was the first image. We were just ecstatic that we had things that were recognizably close to stars. That's the second image, closer, still a little fuzzy. That's the third image. So 20 years, engineering, design, development, integration, all put together. 3 minutes, we got an in-focus image. We couldn't have been more excited. It was really quite a testament to not only the science, but thank you. I'll take that back to the team. Not only to the scientists who had the ideas to build this thing, but the engineers who put it together, all the technicians, all the administrative staff, everybody that is required to bring something like this together. It was a tremendous achievement. And as one of my colleagues said, we are still happy. We're working on things, but we're still quite happy. So now I'd like to show you some of the first things that we did with the telescope. These are early images that we produced so that last summer, June, end of June, we could show the world what we were up to and how things were working. These are not, we haven't quite started the full survey yet, but these were the first examples we could do, even while we were commissioning the whole system. And this is what we called first look. Some of you may have seen some of this. This is a beautiful pan and zoom around a region in the sky called the Virgo cluster. And it just shows a tremendous amount of diversity of galaxies, galaxy types, old and young, and billions of stars, well, not billions in this image, but many, many stars and galaxies. This is the largest galaxy in that area called M49. It's about as big as the Milky Way. And you can see as you zoom in over this wide area, you just see more and more detail, just exquisite number of objects. I'll let it play one more time so you can have a good view of it. This is about 14 degrees on the sky, so something like this. Virgo's actually up right now. You could go outside at night and view this area of the sky. One of the things you see is, I guess we'll just move on. So this is a blow-up of that region, and one of the things you see is this immense diversity of galaxies. We'll use that diversity in shapes and colors and sizes to understand about things at different distances away from the Earth, and therefore the history of the universe. You can see this is just a little chunk of sky in this one larger image that we took. There's about, in the full image that you saw in the video, there's about 10 million galaxies. That's about 0.05% of the total number of galaxies that we will observe with the survey. In fact, that's more objects than there are humans on Earth. For the first time in history, we'll have done that. About halfway through, or maybe a little more of this year when we start the survey, we'll have observed more objects in the sky than have ever been observed in total with all the telescopes in history of humanity. That tells you something about the grasp of this instrument, its wide field and ability to go deep. If you think of that little square that was that one piece of sky with so much going on, interacting galaxies, galaxy cluster, big spiral galaxies, that's what it looks like on the focal plane. So it's just a few detectors of what one image contains that we're showing you here. And again, this full image would be these 400 ultra high definition televisions if you wanted to see things pixel for pixel. It's about 40 full moons would fall in there. So all of you are familiar with the moon on the sky. 40 of those is how big one of our images is. If you saw the first look presentation or have been in science news or looking around at sciencey things, you've probably seen this image. It's not really the core science of Rubin, but it does show the power of Rubin to gather a large field of view, go deep and show a lot of detail in just a few short hours. This was about 7 hours, I think, of data totally taken. It's called the Trifid and Lagoon nebulas. And I'll show you one more video from first look. What we're going to see here is we're looking out at the same part of the sky, but instead of looking at the deep galaxies and trying to understand the deep universe, we're looking for things that are moving in front of us. These are asteroids, things close by in the solar system. So what you're going to see is how we could pick out from each part of these images, and we had to observe over a number of nights, right? Because to find an asteroid, you need to observe it once, then you need to see it move, then you have to develop kind of a tracklet for it and pick it out of all the future images so you can develop its orbit. So you're going to see that here kind of visually. Just looking at the sky, then pulling out individual detectors, there's something that's moving over the course of a few nights. And there's another one, and another one, and more. So in these few nights, about 7 nights, the total number of hours was much less, but over about 7 nights, we discovered 2,000 new asteroids, objects in the solar system. That's about the total number that all astronomy is finding per year right now. This is an animation of all those projected orbits from those 2,000 that we found moving across the sky. And now what you're going to see is move out, project that on the sky from the perspective of the Earth's orbit and the main belt of asteroids. You can see we've only just scratched the surface of what we'll do over the next few years. It's a 10-year survey. It turns out that we'll hit many of these new millions of asteroids that we expect to discover in the first few years. So one particular thing that'll be generating a lot of science early is the study of the solar system. Let me just say a few words about the main science cases that we use to help develop this whole system and that the team is still working on developing and preparing for as we start the survey. There were 4 main science pillars, and by designing a survey with these pillars, we've enabled a whole bunch of science that will be allowed to be done. The science case here has been developed over many years, but it's still quite relevant. So we're going to work on dark matter and dark energy. This will be the next large galaxy survey that we can use to take our understanding of dark matter and dark energy to the next level. The Milky Way structure and formation will observe a much bigger volume than has been available before. Of course, the solar system census that I just described. And changing of the night sky, this ability to take many images very rapidly and then night after night go back to the positions on sky and find things that have changed and moved. So just a few words about dark matter and dark energy. If you think of the mass energy budget of the universe, that's kind of everything in the universe. 95% of it is things we don't really know what it is. We've actually gone a long way in characterizing it and understanding what it's doing or what we can observe from it, but we don't know what it is. And so Rubin is a so-called stage 4 dark energy experiment. We think in astronomy of discovery, but in DOE and high energy physics, we think of experiments. So this is a very planned, dedicated survey experiment to do the next galaxy survey to understand what dark energy is. We can use the same data to understand the distribution of dark matter across the universe as well. And so that will be a combined cosmological result from the DOE side, basically. Milky Way structure and formation, we will observe a volume about 1,000 times larger than we've been able to do before, not only in the disk of our galaxy, but also in the very faint and extended halo. We'll be able to find tracers that will allow us to understand the shape of the galaxy and something about its formation history and then how we think it might evolve. It's also something that we can use as a template for understanding other galaxies further away where we don't have this much detailed information. And similar case with the solar system, we'll be able to analyze a huge amount of data that will divide these asteroids into different categories that have different impact on the development of the solar system, its formation, and its history. It'll also be able to tell us if there's a near-Earth object that might be coming toward the Earth, maybe even hitting the Earth. These aren't really huge things, but they're big enough that we want to know about them before they would get here. Possibly we could even intervene, but at least we would have a lot of warning. And then the changing night sky. As we've talked about before, we'll be able to difference current images from a template image and find things that have changed in real time. We'll be able to do this every minute. So we'll be taking an image every 40 seconds, we'll be sending it to California to process, and we'll generate alerts that come out of that individual image, about 10,000 in any given image. That adds up to about 10 million alerts per night that will stream out to the community they can use those alerts to go and do follow-up with different telescopes. This alert stream, we produce it. We generate the alerts and identify the objects that have changed, but we don't then follow them up ourselves. Other telescopes follow them up. So the community of scientists will go to what we call community alert brokers. We stream that alert stream out, much like you stream a movie to your home, to these specific 7 brokers. Those are places where astronomers and scientists can come and filter the alert stream and say, I want a class of objects that behave like this. They change in brightness over such and such time scale. They have these colors. They're in this part of the sky or this galaxy or this other place. And then they can pick out the few things that they want to concentrate on. And then they can literally go and follow them up with another telescope. One such follow-up network of telescopes is based at Noir Lab, the organization I work for. So these are other telescopes that are in Chile, and we can use them in a coordinated way. So a scientist can say, I want to do this science, I have this program, give me time on this range of telescopes, and then literally almost in real time, as the year goes by, they can be paying attention to the alert stream, picking out the things they want to observe, and then sending those observations to these different telescopes. So they really get control of their own program and decide what to observe and where. It's always the rarest of the rare that are going to get observed because we produce so many alerts, there aren't enough telescopes on Earth to follow them all up, right? So it's a statistical thing. You want to find a class of objects and study a few of them. One of the things that's very rare that even Rubin, with its systematic survey of the sky, has to pause and go off and do something else, are what we call multi-messenger events. So these are things that happen, and we find out about them from some other messenger besides light, besides the photons that we normally collect. Could be gravitational waves, for example. Could be neutrinos. In some sense, an asteroid heading toward the Earth could be a multi-messenger, right? It's a different kind of message. And so often these are very well known, and they have high signal-to-noise event that happens, but we don't know where it's localized. So a gravitational wave detector doesn't have the ability to focus on a very small point in the sky. So you know a gravitational wave event went off, but you don't necessarily have a telescope that can quickly go and find it. Rubin, because it has such a wide field and can move so fast, can go in the general area, do a quick scan, and maybe within hours, find the object, send that out to the community, and then they can go follow it up with other facilities. One such object that's of great interest are things like coalescing neutron stars. It turns out this is the cosmic event that produces the heavy metals that we see on Earth, so gold, for example. That comes from an event like this, what we call a kilonova. And then maybe one of the most exciting things is we can think all we want about things we kind of know and we want to know more about, but there's things out there that we maybe have never seen before. Rubin will be able to see the whole sky so fast and so often that we expect it to find very rare events at different time scales. So it also observes on minute time scales, then it goes, it observes the field again, then maybe a half hour later, then maybe the next day, then maybe next year. So there's all sorts of time scales of discovery that will be enabled by Rubin's survey. And we expect that we'll find things that we haven't seen before. We haven't started the survey yet, we're getting close, but we are starting to put out a little bit of science this year with our commissioning data. One of the things that you may have heard about in the news is the interstellar asteroid or comet called 3I Atlas. So this was discovered by a small telescope. It's an object that comes from another solar system. We know of 3 of them now, 3 in the last roughly 10 years. This one came this year, zipped in, it's on its way out of our solar system now. And you know, it's important to get as much observations as you can on these things. They're very rare and they're very interesting to understand what's happening in our local area. Rubin will be, since it's so can find things even earlier because it has this big aperture telescope and wide field, we'll find maybe 50 of these in the 10-year survey. It turns out that as they announced this observation and this interstellar object, that we had been observing doing commissioning work on the sky, And we said, well, Rubin covers so much sky so quick, let's go back and look at the data and see if we observed it. And it turns out we found it in our data from 10 days before it was announced, because it was so much fainter. That actually is very useful information, those prior 10 days. I want to talk a bit more about the data. I said earlier that Rubin is a full system. It does one thing, it surveys the sky. It's not just the telescope. We have a telescope with a giant camera, and then it's producing a huge amount of data, and you have to have a real data management system able to handle that, to do the science with it. And this is, after all, science at scale. Rubin really is astronomy at scale. We're going to have the largest data set in optical astronomy ever produced, and it will push us in ways that we've never been pushed before. We started talking about how things started out in the 90s, right? We were still sending movies around in the mail in the 90s. Now we obviously have much more powerful computers. We have a very high bandwidth network, and we have advanced algorithms that have come a long way in the 20 years that we've been developing this program. Just wanted to say a few words about how we get the data where it goes. So the data capture, of course, is on the mountaintop in Chile. We have a redundant, high throughput network. It's about 100 gigabits per second dedicated to Rubin. So we can get our images to California, where they're processed in about 10 seconds. That's actually a little bit out of spec. We want to get them there in 7 seconds, so we can do the processing and push the alerts out in time. We're working on it. It should be good. The network's been very stable. And then over time, as we process the data, so that's the nightly data, but we collect data for a year, and then we think about, let's process that year's worth of data, make catalogs and deep images, and put them out as a data release as one coherent set of data for astronomical study. It turns out that once we get ready, we do a ton of tests, we freeze the pipelines, we look at what they're producing, and we finally say, yep, it's good to go, let's do it. It takes about 9 months to process that year's worth of data. And so we need help, and so we've got help from our colleagues in the UK and France. So we have 3 data facilities, California, UK, and France, that will all chunk on this data for about 9 months. It'll all come back to Slack, and then we'll make it available to the community. So that every 40 seconds, 3,200 megapixel image results in about 10 terabytes of data every night for 10 years. It's 30 petabytes of raw data over that period. That's 15 zeros, I think, and a 15 petabyte catalog. And that's just the raw data. When we process it, we make lots of intermediate data products, and we combine the images in different ways. By the time we're done, it's about 500 petabytes in 10 years. And the point is, this data is not just for the scientists, but it's for everybody, and we can make it available to everybody. And it's so much data that we don't conceive of the astronomers taking the data home like they do with many telescopes now. We bring the scientists to the data. We have what we call a science platform that runs on the Google Cloud, so anyone who has the rights to access this data as a professional astronomer. That's actually all the scientists in the US, all the scientists in Chile, and named scientists in our collaborating countries overseas. They can log into this science platform on the cloud, and they can access the data. They can go through a portal and just kind of scan the sky and pick out images or data that they think are interesting. They can use Jupyter notebooks to do more detailed analyses, and they can even run APIs that automatically connect to the data and do large processing jobs, batch jobs. All of that is just the start, right? Then you actually have to analyze the data and pull the things out statistically and find the rare objects. And so we've used the 10 years, 20 years of development to build that type of pipeline, that type of capability within our science community. And they're getting ready now to do it, so they can find the rarest objects, and they can analyze billions of objects. These billions of objects, I said, maybe I didn't say it, I said more than the number of humans. We expect about 20 billion galaxies at the end of the survey, and a roughly equal number of stars. And that's trillions of observations. So those are the objects, but we observe them many times. That's trillions of observations in this database that people need to be able to manage. We're really proud of the fact that Rubin should democratize science. It can provide the best data in astronomy to anyone. You don't have to be part of a big school. You don't have to have your own telescope. if you have a good internet connection, you can access this data and do science. And so it's going to enable folks from all over the world, from all different backgrounds to do that. And we even have a citizen science pipeline. Many of you know what citizen science is, where you use large data sets and you hand them off to groups of citizens who help you classify or characterize them. We do the same with astronomical images. But we actually have a pipeline that actually can have a real scientist or a professional scientist manage what they want to do with that, and then it actually makes that happen by sending the right data over to the Zooniverse where the public can connect and do that. We connect with the public, which is super important now more than ever, as I said before, through our public outreach, education and public outreach program. This program was built from the ground up as part of the construction project. It's not an add-on. Everything about it was developed alongside the system itself. And now it's happening. And so we have formal education where real Rubin data will flow into the classroom through a web portal that teachers can get with us, understand how to use, and then take to the classroom to do regular lesson planning. We have a tremendous amount of outreach materials, mobile-friendly apps, website, visuals, social media, interactives and videos, and then, of course, the citizen science program as well. We actually, with the commissioning data, have started the citizen science program. There's one called Rubin Comet Catchers, so this helps a team of people interested in studying comets by finding comets and helping to classify things that are not comets but might look like them to a machine algorithm so they can feed that back into their algorithms and have a better sample. The same is true with what we call the Rubin difference detectives. I talked about the subtracting of images and finding things that had changed in the night. Well, sometimes when you subtract an image, you get a lot of junky artifacts that aren't real, right? But they look like a big spike in brightness or something. So we hand them a bunch of these that some are real and some are fake, and they tell us which ones are which, and we can use that to train our algorithm so it does a better job providing only real transients and real variable objects to the science community. So we're almost there. I just wanted to give you a few words about what's up next. We are in the early operations phase. We are still optimizing the whole system. So we know the system works. We know it takes great data. You've seen some of the data. We need to make sure it works that well all the time, every night for 10 years. And so we still have a few things we're working out and optimizing it. In the meantime, we've taken this huge amount of commissioning data and we're going to put it in as a science data preview to our community in a few months. So this is a large job. It's not as big as our annual data releases will be, but it's pretty big. It's the first giant data set from the LSST camera that our science community will get to use, and they're really excited. We're really excited to give it to them. That should be out in a few months later this northern summer. This alert stream, this streaming of detected objects all night long is going to start very soon. Watch the media. You'll hear about it real soon. And then the survey, we hope, will start a little bit after that. We're still not quite ready to decide to declare the actual day yet. So it's all happening, and I hope that you've got a little bit of a sense of what we've been up to and how you can actually be involved or engaged or follow along as we go for this. I want to leave you with a quote from Vera Rubin herself. She says, "Don't shoot for the stars, we already know what's there. Shoot for the space in between, because that's where the real mystery lies." And we really take that to heart. We can't wait to get into these images and dive deep down into them in those spaces where maybe you wouldn't normally look, and see what we find. Thank you very much. Okay, I think Jennifer Wiseman's going to come up, and we're going to carry on this conversation for a little while longer.
All right, that was just super. And when you, Dr. Blum, when you showed that image, I think somewhere it's been called cosmic abundance or something like that, of that image just filled with galaxies swirling around, some of them interacting with each other, with stars. We were sitting there watching and we said, really, there's nothing else to be said by the rest of us, you know? That just basically tells the story. So that's just astounding. So congratulations. Thank you for sharing some of this opening new science from the Rubin Observatory. And I did want to point out, while we're honoring Vera Rubin, I believe there's a U.S. minted coin
There
now
is.
in her honor. So, you know, we can all get this coin. I don't remember if it's $1 or a quarter or whatever, but it's in her honor and worth obtaining. Okay,
Just go to the U.S. Mint online, and you can get it.
All right, U.S. Mint online for the Vera Rubin commemorative coin. Okay, so I want to ask you a few questions.
Okay.
One is it's how we actually got this observatory, because you showed us the napkin.
Yeah.
And that's so classic. Like, that's what people think scientists do, and we actually do, you know, so it's kind of amazing. But there's the scribble on the napkin, and now there's the observatory.
Yep.
What came in between those two? In particular, you know, was this observatory, was this large facility recommended through something like a decadal survey or something? How did it get advocated up the chain to the point where it was funded and constructed?
Yep. So that's an excellent question, and it did take a long time to get from the napkin to the telescope, more than 20 years. And so after the napkin was you know, generated the suitable excitement that this is something we could actually do, then groups of scientists got together with groups of engineers, and they started prototyping things, developing things. That was probably the first 10 years or so, building up a real design that would work, that was costed, that could show the funding agencies that we knew what we were doing. That probably led us up to about 2010. And you mentioned the decadal survey. That's a process that maybe not everyone in the room is familiar with, but astronomy and astrophysics goes through a decadal survey where the community gives input, and eventually that input is taken by a group of experts listening to the community, and they decide what are the highest priorities for the next decade, both in ground and space. So if you're a ground-based telescope like Rubin, you want to be recommended coming out of a decadal survey as the number one project, and that's actually what happened in 2010. So there was a huge amount of development work that was also supported by private philanthropy. I didn't mention it, but I should. The mirror, the main mirror there, is one of the things that always takes a telescope project the longest to get going. And we received a very generous grant donation from the Charles Simoni Foundation. Charles Simoni, you may not know the name. He's, you know, if you use Microsoft Office, you're using something that Charles Simoni developed. He and the Gates Foundation, or Bill Gates personally, I think, gave money. They allowed us to get the mirror going before we had federal funding to build the project as a long lead item. So that kind of thing was going on. Scientists were honing the science case. We were understanding what it would cost and what it would take to build it. That all led to a convincing case at the decadal survey. And then it took a few years before the NSF and DOE kind of ingested all that and took it on board and found the funding mechanism and the way to go forward. And they eventually both put it into their large construction queues, and we started construction in 2014. So we actually had a little bit of work going on the site before that. We had the mirror going, and we had some other development work, also supported by the National Science Foundation and DOE. But the construction funds came then, and so it's been a little over 10 years now, getting from the start and building everything. That facility was probably done in 2016, maybe. The facility up to the dome,
Okay.
not the dome and the telescope. The telescope, the giant steel structure, was delivered not that long ago. And then you saw the final subsystems, everything coming in the last few years.
Right.
Yeah.
Okay, so I wanted to ask you a little bit about your personal background. What brought you to this role? As I understand it, you were first trained as an engineer, and then decided to become trained as an astronomer, and all of that seems to be very important for this role. So can you tell us a little bit about what drew you into this role in this project?
I actually was talking to a group of students on Zoom the other day. These are students that are studying, might become astronomers, they're undergraduates, they're having a research experience in Chile at our facilities down there. And they asked me the same question, and it's a good question. I think there's many different paths to become, get into astronomy and then get into leadership of a project. But it's definitely probably true that all of us start focused on science and focused on doing research. And I think it's important that a leader of a scientific institution have that background so they understand the actual operation and development of the program. But then at some point, something comes up, an opportunity, a desire to serve, whatever it is, and I think there is a conscious decision that says, yeah, I want to step up and give back and do something for the community, or no, my best way I can get back to the community is to keep doing top-line research and really, maximizing what comes out of these facilities. I made the conscious decision at one point, an opportunity came up. They asked me to do something, not lead an observatory, but take on a big project in the observatory, and I said yes, and then one thing leads to another, and you keep going.
Okay, but let's back up even earlier.
Okay.
Why did you choose engineering, and then why did you choose to also add to that a degree in astronomy?
Yeah.
What made you interested?
I think as a younger person and in high school, I was interested in solving problems, and I saw how you could use math and engineering principles to solve problems. And I was always interested in space. I remember the first moon landing. I saw it live. And I thought I would love to do something in space. And so I was really focused on getting a degree in aeronautical engineering. I did that. And then I worked at the Boeing company, and that was fine, and did things. But then at some point I was like, this is great, but I actually liked the parts of engineering that were more development and more theoretical, maybe, I'm not sure. And I had a strong interest in space and astronomy, and so I decided to go back to grad school. And I was extremely fortunate to have a family, including my wife, who were willing to support me in doing that.
Yeah, well, it seems like this project has been very intense in engineering, as well as science, and so you're perfectly prepared for this role.
I think a technical background is like, this is an interesting point, right? We often hear in astronomy, who's going to build the next generation, right? Because you work at NASA, that a lot of folks never go to a telescope. They can get data provided to them. We're now providing the biggest data set ever directly to people. They don't have to go to a telescope to get it. Yeah. But we still need people to build telescopes and instruments. And so I think developing technical workforce and continuing to put them in is absolutely key. From my background, having an engineering background and then an astronomy background, I think it is useful in my position. If anything, it helps you ask the right questions of the team at different times.
Yeah, right. Great. Okay, so let's talk about that. Astronomers use telescopes on the ground and telescopes in space. And I have used myself telescopes on the ground and telescopes in space. But people may ask, why do you need telescopes on the ground as well as telescopes in space? Do you have an answer for this? Why not put the Rubin telescope in space?
Actually, that's a funny story. Some of you may know that astronomy, ground-based astronomy in particular, is. I will answer the question, but I'll get back to it. There's something happening in low Earth orbit right now, which is giant constellations of satellites being launched, and they will have some impact on ground-based astronomy. How much, we don't know. We've actually worked quite closely with some of the satellite makers, and it's been useful. I have no doubt they will continue to make and launch satellites. They're not going to stop making satellites. But
You're
having
talking about the streaks.
yeah,
that
the
those
streaks that
satellites
are
make.
artificial. They will block other light or
your-
provide
yeah.
systematic impact to our data. But anyway, so we work with them to try and actually mitigate the brightness of the satellites. So at least it's a brighter thing. It doesn't saturate our detectors, for example. Anyways, the funny part was at one point, one of our folks, actually I think it was Tony Tyson, who I showed you a slide of, was at SpaceX talking to them. And I believe Elon Musk said something like, well, we'll just launch your telescope up into space. That's not, it's certainly, having space-based telescopes is a great thing, but there's many reasons to also have ground-based telescopes. You can do different things with them. So to answer your question, we actually have 3 major missions doing some similar science, 2 in space and 1 on the ground. That's Rubin, the Euclid mission in Europe, and the Roman mission that was mentioned here, that's NASA, that's going to be launched very soon. The short answer is they're all complementary. If you combine the data that you get from all 3, you'd learn more in different things. And in this particular case, you can actually look at the science cases of those 3 missions and say they really rely on 3 things. They rely on a wide field of view, they rely on going very deep, and they rely on the best image quality you can get. And all 3 of those try and do their best at all 3 of those missions try and do their best at all 3 of those things. But it turns out that the 3 missions, just the way they're designed and the limits of what you can do, they really all just do 2 of those things well. None of them does all 3 of them well, right? So Rubin goes wider and deeper than anybody. Euclid goes wide and has good image quality. Roman doesn't go quite as wide, but it goes deep and has great image quality. So we're spending a lot of time actually with our colleagues on both those missions, trying to understand in the near future how we can put the data sets together and combine them for our scientific communities and do even more science.
That's awesome. So in case anybody doesn't know, what Bob just mentioned is that we have another large space telescope being launched this fall, the Roman Space Telescope, named after another wonderful pioneering astronomer, Nancy Grace Roman. And she was working at NASA headquarters back in the 1970s and really advocated the idea of a space telescope. So she's sometimes called the mother of Hubble. But the Roman telescope will also be one of these wide field survey instruments. Roman, I believe, is going to be focusing on infrared and red wavelengths of light, whereas Rubin is really more of a visible light optical observatory, right? So that's another way of complementing. Okay, so let's talk about the science. Okay. First of all, let's talk about this wide field. One of the reasons I understand you want a telescope that can see this wide field of view is that you can see how galaxies are distributed. Mm-hmm. And that helps us understand something about dark energy and the interrelationship of dark energy and dark matter. Right. Is that right? And do you have a quick way, because some people have been asking me, even here at this meeting, who are not, focused on astronomy in their own work, what's the difference between dark matter and dark energy?
Sure. So the difference between dark matter and dark matter is some massive particle that actually gravitates, and we can see its effect on the motions of stars and galaxies, for example. So we know it is a physical matter. Dark energy is the word we use to describe a phenomena that we observe. What is that phenomena? It's that as we look back in time and we use tracers of the expansion of the universe, not only is the universe expanding, that is getting bigger in time, but it's doing something completely unexpected. It's accelerating in that expansion. Normally, when something expands and gets less dense, which is what's happening to the universe, it would contract. We had thought that the matter in the universe would pull the universe back, but instead what we find is it's racing out faster and faster as time goes by. So it's kind of like a negative pressure is how you could think of it. As things get less dense, it gets pushed out even more. But the reason why astronomy and astrophysics is the best handle on both of these things right now, there's actually really well thought out and ongoing experiments that may show us what dark matter is, what particle is involved with dark matter on the ground here on Earth. But they're pushing against limits that they're only finding upper limits right now. They're not finding what it is. What we can do is we can use the position of galaxies across the sky and in time or redshift or how far away they are to make a map of the universe, and we can compare that to a cosmological model. So we can use the galaxies as tracers of what the universe is doing. And because we can get information about how far different galaxies are away from us, we can also get the other axis, okay? And we can compare that to a cosmological model with more or less dark energy, and we can try and constrain it. The dark matter is actually gravitates. So what you see is clusters of galaxies being pulled together over time, because the expansion of the universe is, we're not talking about galaxies moving out in a void faster and faster. We're talking about the universe itself expanding. And so if there was no gravity, the galaxies would still stick with the universe and expand out with it. So you have two things going on. The universe is expanding itself. Space-time is expanding. And then you have galaxies and matter inside that because they're attractive, they're starting to get more and more dense. They're pulling things in, forming these large filaments of galaxy structure, galaxies and stars. And so you can use our observations of billions of galaxies in a statistical sense to identify how much those galaxies have gotten more gravitationally bound to each other. And how much they have depends on the expansion of the universe itself. And so you can use them both to understand the current cosmology.
So Rubin, by measuring and seeing this distribution of galaxies, both in three-dimensional space but also in time,
Right.
tells us something about how the interplay of unseen dark energy and unseen dark matter, but how they've interacted with each other basically to create the structure of the universe over cosmic history. Is that right?
That's right.
Okay, that's awesome. So
I want to say one more thing.
Yeah.
The other thing we can use Rubin and that we're designed it to do is actually to very precisely, well, in a statistical sense, measure the shapes of galaxies. So it turns out that as the light from a distant galaxy travels to the Earth, that light will pass through all this dark matter. And every time it does, it gets deflected. Just like, if you throw a baseball up, it gets deflected by the Earth's gravity. Light will be deflected by the gravity of objects between where it was emitted and where we see it. Yep. And so what happens is all those little smudge galaxies that you saw in that image are slightly distorted. And it turns out you can use the systematic distortion of galaxies in this part of the image and this part of the image, and you can back out how much dark matter it would take to arrive at that distortion. And it's a very, very difficult measurement. We've done it on multiple telescopes. We did it in a big way on one of our other telescopes in Chile as kind of I don't want to call it a test case. It was the next best thing you could do. And now we're looking forward to Rubin taking it to the whole sky.
that's awesome. I was also amazed by seeing how many of, pulling back now into our own solar system by using the universe as a backdrop and then seeing these transient objects just moving, relative to the background objects. You're already picking up so many of these objects. That is going to transform our understanding of the solar system, right? And we had a session right here at the AAAS meeting this week about near-Earth asteroids and the near-Earth objects and the efforts that are being made using facilities in space and on the ground to try to find these things, track these things, understand these things to kind of help mitigate risk. And so it sounds like Rubin will also be a part of that network. Is that correct?
That's right.
Yeah.
So both NASA and now NSF and DOE through Rubin are going to find a tremendous amount of near-Earth objects as we go forward. And
Yeah.
we should be able to detect the vast majority of them between the two.
And I loved the observation of the interstellar comet. I
Right.
mean, so I think we'll be seeing more and more of these objects that are whizzing through our solar system that actually originated from somewhere else. That's pretty cool. Let's talk a little bit about big data. You mentioned it. That's really impressive. And so we're going to have this basically shower of big data coming from Rubin and some sort of pipeline so that people can access this data. But things are changing very quickly. You know, we're having artificial intelligence and the use of it is growing at a skyrocketing rate. So do you think that the actual method of handling this data is going to be evolving as the mission continues? I mean, there must be rapid advances in handling big data. Will you be changing and evolving the method of handling your big data along with these advances?
I think there's a number of places where we'll see AI have a big impact on astronomy as well as the rest of the human activity. I don't think there's the basic taking of the data and processing it into images and catalogs. I don't think there's a lot of room there for improving. There might be some, but that's pretty set. It's really how you analyze this large data set, how you comb through images. And so a lot of the thinking leading up to Rubin was that the catalog would provide statistical data sets that would teach us so much, and I think it still will.
Yeah.
And the images were what were the source of the catalog. Of course, what AI is good at in machine learning is looking at images and shapes and things and drawing conclusions from just learning what's in those data. That's the thing that's changed from how we imagined this going 20 years ago. And that's the thing that we're trying to catch up with. And in fact, we are. And many of our people in our community are working on techniques to take Rubin, to define specific Rubin data sets, like a certain class of galaxies or classes of galaxies that can be trained on AI ML and then used on further analyses down the line. We know that the need for compute power to do these things is probably greater than what we currently have, and so we'll be thinking about novel ways of trying to get more and more compute power, more GPUs. We don't have any GPUs in our current plan, and that's coming. We're going to have to think of taking advantage of the other DOE labs' computing resources. We have a number of international in-kind contributors who are setting up computing centers and data centers for us to access and use, or for our community to use. That's another way we can expand that. The other place where I'll say we definitely will see changes is we have lots of control loops in the system, right? I didn't mention it, but the main mirror has like 160 actuators on it that are constantly moving, changing the shape to adjust for gravity and thermal changes. The secondary mirror has another large number of those. The camera has things that move it around. So there's control loops all over the telescope, and we're actually developing things right now that we could probably take on Sky very soon that are AI-based control loops instead of your standard control theory that tells you how to set the mirror based on certain inputs. The AI will do it for you, and maybe much faster, and so that's really interesting. We have a huge body of information, technical information and history of building the telescope and how we use it that is very hard to find, right, unless you know exactly what it is. But we're starting to build, based on chatbots and things, augmented with our own data. We're starting to build tools that we can use right now. They'll get better. That a human can just ask a simple question like, how do I fix that system, that's up on the top end of the telescope that controls X, Y, or Z? And it will go through our information and give you a quick answer. So that's coming.
That's super cool. Okay, I just want to make sure I understand I have a few more minutes based on my instructions. So I'm going to ask you a couple more quick questions before we wind down. according to my latest instruction. So one of them is, we've got a lot of young people here from various fields of science, engineering, science advocacy, science communication, science policy, science support. How can people, especially early career folks, get involved in Rubin or something like that, either as astronomers or maybe people not directly involved, but they might want to access the images or something like that?
Sure. So I think Rubin is evolving along a model that really started for us with high energy physics. You know, the old school astronomy model was, this is something Vera Rubin fought against her whole career, was, oh, if you're the right person at the right telescope in the right university, you get all the nights and you can decide who gets to observe, you know. Rubin will make data available to anyone no matter where they're at. And the Rubin Science Collaboration is open, that anyone can join it if they want to work on Rubin science. They can get involved, and all it matters is that you put in the effort to contribute to the collaboration. So that collaborative work where you have big projects, this came from the accelerators and that kind of thing, right? One or a few people couldn't do a whole project and understand all the data and put it all together. It's much more collaborative. So that's where Rubin's taking astronomy. There's other programs in astronomy that are doing the same thing. So as a young person, it's pretty exciting because you don't have to have all the ideas right off the bat. You can get involved with other people who can show you what's going on, and you can get help, and then you can start contributing in any way that fits your skills and your desires. I think this collaborative way of doing astronomy is something that I've seen change over my career. When I first started, you know, you had to write telescope proposals, and if you didn't get time, you were kind of out of luck.
Okay, last question. What are you most excited about? We know that this survey is going to take years to actually build up the deepest, most sensitive images, but we've also seen that you're already getting some really cool data. So what in the near term and what in the long term are you most excited about coming from the Rubin Observatory?
Right. Scientifically, I think I am most excited about the possibility that Rubin's capabilities will open up this phase space of how bright things are and how fast they change. And so that phase space is big, and we know where lots of things live in it, like supernova and variable stars and kilonova and even coalescing neutron stars. But there's big parts of it that we don't know anything in there.
Yeah.
And Rubin will observe on timescales that should find things in that space. And so I'm really excited to see what we find.
Awesome. Well, I am thrilled that this observatory is online. I think this is an example of a basic research facility that's going to open up new discovery like never before, and many of our other astronomical facilities will follow up on the detections from Rubin to get more detail. And I think this is an example of why basic curiosity-driven research and exploration is so important for science and for the human spirit. And so we all need to keep advocating for the importance of basic exploratory science. Let's thank Dr. Blum for his wonderful presentation.
Thank you.
And I think we're going to be we're welcoming now Dr. Maldonado to come up to the stage. We're going to exit and appreciate all of your attention this afternoon. All right. Thank you.
I don't know about you, but that was a real treat. Thank you so much, Bob and Jennifer. I am not tired. That was amazing. So we're at the close of this amazing meeting. I had a great time. Friends and colleagues, I could not be more grateful to serve as your president and chair of this meeting. And I hope all of you are also feeling a sense of renewed vigor and excitement about science and how all of you have a voice in our future this year and beyond. I want to once again express my deepest gratitude serving as your president. Sudip, thank you. What a wonderful partner, and the fellow board members, thank you. And not to mention, and not to forget the AAAS team. They are extraordinary. Thank you so much, all of you. They are very patient, extremely talented people. Now, it's my pleasure to pass the baton. It's that moment, and I could not be more excited to pass the baton to my dear friend and colleague, Marina Picciotto, from whom you'll hear momentarily. Marina is a rock star in neuroscience, but she is also one of the most humble, approachable, and engaging people with a great sense of humor. I'm excited to continue our work together for AAAS in the year ahead, and I am pleased to invite her up to the podium and introduce the theme for next year. Marina.
Thank you, Teresa. Can we have an enormous, like, don't hold back, round of applause for Teresa, please? Yeah, I like that. Yes. I loved her address on Thursday. I thought that her story was inspiring. It's been inspiring to work alongside her. And it's really been a terrific conference due to her leadership over the last year. So this is going to be something that we continue as a partnership. It's pretty cool being able to sit next to her. I keep looking over thinking, why am I in the room with this amazing lady? So it's really fabulous to have her as a colleague. So I am pretty excited to work with you guys as the next president. Did anybody have a good time? Anybody learn anything? I did. So my job tonight is to introduce you to the theme of the 2027 AAAS annual meeting, and I can't promise you good weather. It's in Chicago in February. But I can definitely promise you engaging discussions. I can promise that you'll run across somebody in a hallway, hopefully in an elevator, who will, so prepare your elevator pitches, that will give you something to think about, that will perhaps turn you in a new direction, and help you find some exciting new twists in your work. So I think we get the new logo coming up. Yes. So the theme is Science Forward, and particularly how science and the kind of amazing deep science that you heard about today allows us to engage with our world around us, with policy, of course, but also education, your family around the dinner table. The world really can benefit from your science and your focus. You may not be the person who looks out and goes out and talks to school kids. You may want to stay in your little bench and look at your molecules, but at least find someone here that can talk about your work in an engaging way with the rest of the world. So I hope you'll join us February 18th through 20th in Chicago for Science Forward, Policy and Engagement for a Changing World. And in this era of really rapid and often unpredictable change, science has a responsibility not only to advance knowledge, it also has to navigate those pathways that connect discovery to decision-making, to communication, to public trust. And this meeting's going to explore how ideas move all the way through that ecosystem, right? From the beginning of that discovery and how it's then shaped by the intersections of research, policy, media, and society. So we invite all of you, scientists, engineers, policymakers, communicators, leaders across sectors to examine how evidence informs action, and how collaboration built on relationships of mutual trust ensure that science continues to serve society in necessary and transformative ways. So more information will be online at meetings.AAAS.org. You'll have until early May to polish up and submit your sessions and your workshop proposals. I hope that you will think about having a colleague who does something quite different from what you do as part of your team, as part of your presentation. And I look forward to being in touch with you in the coming months with some exciting new directions for the annual meeting. We know that you have a lot of places you could be on Valentine's Day. For those of you who are from my graduate program, I see you there. We used to actually have our recruitment on this day, so the rest of the graduate program is off having a good time on Valentine's Day because we're postponing it till next week. But you're here, and so I hope you'll join us across the street at the Hyatt Regency in the Regency Ballroom. It's right on the lobby level for a reception that we're going to call For the Love of Science, and not with an exasperation in our voices. It's going to start as soon as you leave here, and my deepest thanks to all of you for joining us here in Phoenix, and I really hope I will see many of you, if not all of you, next year, maybe with coats on, in Chicago. Thank you, safe travels, and good night.